today it's my pleasure to introduce our last speaker, Karl-Mikael Perfekt from NTNU, who will give a talk entitled Operators and Embeddings for Paley Wiener Spaces and Convex Domains. So take it away.
Okay, thank you very much. Yeah, thank you very much for the invitation and the hospitality of Isaac Newton Institute. So I'll talk about okay, so I probably have too many slides, but I want to talk kind of about a research program on, about Paley Wiener spaces in higher dimensions that I kind of began 10 years ago or so, but that really took off together with Konstantinos Kostas, who was my very talented PhD student in Norway and who's now a postdoc with Thomas Hiitonen in Helsinki. So the talk will be based on basically three of our, all of them are actually still preprints. So, and two of them are on archive and one. So that, will hopefully be out soon, but I can share if you ask me if you're interested. Okay, so what do I mean by this? Yeah. Okay, yeah, I was planning to write some stuff. Okay, so what do I mean by a Paley Wiener space? So in principle, I'll just take a convex set in Rn, and let's look at the LP functions that have Fourier support in that set. And okay, so if you take an interval, say -1 to 1 or -pi to pi might be your preference, then you get sort of the standard Paley Wiener space, right? So these are, in this compact case, these are spaces of entire functions, right? Although my talk will be very on the Fourier side, so it won't be very complex analytic at all. And then once you go to higher dimensions, it's less clear what sort of the canonical Paley Wiener space should be. One setting is if you just take the product, then of course your new Paley Wiener space is just has a product structure. So that's a simpler case. While if you take omega as the unit ball, you get quite a different space. So in particular, Charles Pfefferman had this famous counterexample showing that, he showed that the multiplier of the disk is not bounded on any, the Fourier multiplier of the disk is not bounded on any LP. And I'll have more to say about that later, and you can upgrade that easily to say that there's no bounded projection whatsoever from LP to the Paley Wiener space for P not equals to 2. And so in particular, that doesn't, maybe you can still interpolate in that scale of spaces, but I don't know how, so I'd have, right? So that's not a tool that's available for me in that setting. Okay, and then, in principle, this makes sense also for unbounded sets, and so that will also be included in the framework. The standard one is, so what I would call the Hardy space, HP, of the upper half plane. So these are LP functions where the Fourier transform is supported in 0 to infinity, right? So in this notation, this would be the Paley Wiener space of R plus. Of course, this behaves differently than a Paley Wiener space, and the reason for, why is it the upper half plane here? Well, if you have a function which has only positive Fourier support, then the Fourier transform will be analytic in the upper half plane. And so you can associate this with a space of analytic functions in the upper half plane. But again, my talk will not be very analytic, but that's sort of the background. Okay, and there's a very well-developed Hardy space theory, and that's sort of my background back when I was a PhD student. And in higher dimensions, okay, it's important there's kind of two different types of multidimensional Hardy spaces. One of them is when you do this, where you just say that one of the variables is positive. And in that case, the space is just like one copy of well-understood HP tensored with copies of L2. So this here, the theory is the same essentially as in just one variable Hardy space theory. The so-called like multi-parameter Hardy space theory, which Robert Pfefferman and Alice Chang wrote a lot about and was a big deal in the 80s, 90s, early 2000s, is this kind of product theory where you consider that the functions have Fourier support in a cone, like in an octant. And this setting, I mean, there is a lot of theory for this that was developed, but there's many outstanding questions and things that we do not understand in that setting. So that'll be reflected also, in the Paley Wiener space of the cube. There's many questions that we don't know how to answer. So I'll get to that later on. Okay, so that's my background. So what I mean with the Paley Wiener space, there's also some unbounded sets in the background. So I'm not going to talk about. So I said in the abstract I would talk about embeddings, and I'll talk about convolution type operators. So I'm going to start with embeddings, but just to motivate what those embeddings should be, allow me to look at this kind of like convolution operator. So if your domain, this is a Hankel operator, but if your domain omega was symmetric around 0, then of course it doesn't really matter whether you have plus or minus in this in the kernel here. So instead you would look at phi hat x minus y. It would be unitarily equivalent if you had a symmetric domain. So this you can think of as sort of a compressed convolution operator. Really, you have to put some shift in there as well to get a Hankel operator. It's a convolution type operator where you, at the end, okay, so you start by projecting onto your Paley Wiener space, you do the convolution or the flipped convolution in this case, and then you project back onto the Paley Wiener space. So this is like a Hankel operator, which is a very classical type. But let's deal with the plus so that we still have an interesting question for the Hardy space. So better to talk about Hankel operators. Okay, so we want to say something about this operator. The easiest thing we can see is when it's Hilbert-Schmidt, right? This is always the easiest question you can ask about any operator, because especially this is an integral operator. So to compute the S2 norm, we just need to calculate this, the double square integral. And if you input, z equals x plus y and make the change a variable, you get this weighted integral of the.
What does not contain in line?
Oh, so it shouldn't be like the upper. Yeah, so it shouldn't be like r plus times r, because this, right? So it should be a bounded set or like an octant, right? This only contains half lines, but not lines. Yeah. So it doesn't include the case that, like the standard HP theory. Yeah, okay, thank you. Okay, so then you get this kind of weight here where you have the measure of this set. What is that set? So if we have like an omega, this set is and then you have a point x. This set here is this is omega intersected 2x minus omega. It's the largest symmetric convex set containing x. It's called the Macbeth region at x in convex analysis. Okay, so when the set has this product structure, then this weight has a corresponding product structure. But of course, if you're like in the ball, this weight behaves, so this is on the Fourier side, right? So these are LP functions with Fourier support. Then the weight on the Fourier side behaves like the distance to the boundary with a power. Okay, so there's many other reasons, but this is sort of one reason why this is a natural weight to put into your Sobolev-Besov spaces in this setting. So I can give you other motivations later, but let's just accept for now. If you want to describe this convolution type operator, you better have something to say about this weight. Okay, so this weight is not a brand new object. So like I said, this weight is called the Macbeth region. It's the largest symmetric convex subset of omega containing the point x. And luckily for us, this object has sort of been studied in the literature. So people in something called economic cap covering. So you're wondering, because you can kind of think of these that instead of this region, you make kind of a well-chosen cut here. So it's related to, studying these sets is sort of related to if you take a bunch of random points and form the polytope inside, how well does that approximate to the domain? Like that kind of question. But anyway, so the weight is continuous, and and by Brun-Minkowski, precisely Brun-Minkowski, all these super level sets that we're going to look at later are, the function is concave, and therefore the super level sets are convex, which will be important for proofs, not in the talk. But, and yeah, you have nice properties. This behaves well under affine maps. Okay, so let me get to the embeddings kind of that I want to talk about. So let me start with one dimension. Right, so I'm just recalling that what's on the board here, that HP is the Paley Wiener space of R+. So the classical Hardy inequality, in this language, in this continuous inequality, would read like this. That if you have an H1 function, so this is an L1 function with positive Fourier support, you have this inequality. So this inequality is not true on all of L1. I think you would have to put L1 log L to make this true on all of L1. But when you're in H1, you have this stronger, inequality, known as the Hardy inequality. How do you prove that? Well, the typical proof is like this. So we have this function b of t, which has a jump. Okay, so, this is the, so I drew the Heaviside function, I guess. But so you have this function which has a jump. So it's like pi I don't know exactly how to make this image make sense, but you understand what I mean. Right, so it's just a sine function with pi I in front. So that's a bounded function. And if you compute the Fourier transform, it'll involve, maybe there's some additional jump, but in any case, at 0, which we don't care about because we're going to see at the positive Fourier support, it'll be like a principal value of 1 over x. So then if you start with so if we look instead at, for example, this inequality, where I have a square instead, then I can look at this as this function b hat times f hat in L2 on the Fourier side, right? Because these functions only have support in 0 infinity, and b hat does coincide with 1 over x in 0 to infinity. So this you can write like that. Okay, but then we can write this as, we can forget about we can move back to the space side where this is just a convolution with b, and then we do Young's inequality on this convolution, and therefore this is less than the infinity norm of b times the L1 norm of f and another L1 norm of f. So you get this inequality kind of, but with a different homogeneity by knowing that you have such a b, such a symbol b. And then to upgrade it from here, I wrote inequality with square. To upgrade it to a power 1, you typically use this factorization that any H1 function can be written as a product of two H2 functions, and then you do Cauchy-Schwarz. But that's kind of a deep Hardy space fact. And for the spaces that I'm interested in, we do not know if that is true. I said that there were unknown things about the Hardy space, and that's one of the main issues, whether that kind of thing survives. So this thing is not a thing that we have available, this factorization, but that is the typical proof of the Hardy inequality. And then another important inequality is what we kind of call the Helson inequality, which was given a very nice proof in my kind of Hardy space language by Dragan Vukotic. But this is really the Karl-Mikael inequality, which is precisely what I wrote here. But here I got it with a worse constant, right? Here I got it with pi, but actually this inequality is true with 1. And actually, if you put f as like the derivative of a conformal map of the upper half plane to domain omega, this gives you the isoperimetric inequality. So this is a inequality that I guess you're all friends with in a way, just to try to motivate this. Okay, so for the first part of this talk, I kind of want to talk about this in this higher dimensional Paley Wiener setting. So, okay, so at first we could have it as completely possible as general, right? Instead of just having L1 here, we could have LQ, and we can put power P, right? Here we have the power 1 and 2, and okay, and then you can ask for which D you're interested in this. And okay, and maybe you can interpolate between inequalities and stuff, so it makes sense to have a wider range of parameters. I'm not going to go into that, but you can fairly quickly see, or yeah, it's not so, you can see anyway that it's necessary always, no matter the domain, to have these inequalities. So Q has to be less or equal to 2, otherwise yeah, it doesn't work. P has to be less than the dual index of Q, right, like the Hölder conjugate. And also you can see by testing on a box in the right, in like a level set of this, you can see that this D has to be less than this kind of, I don't know, critical index. Or
again, what is the omega?
yeah, so that's the weight. That's a good point. So that's kind of the weight that it appears in many ways in the setting, but like if we start with this operator, this is the natural weight for just the Hilbert-Schmidt class, and we'll see that it later be the natural weight for SP in general. So yeah, that's a very good question. So we start with that, and then yeah, and okay, and I'm looking at these. Okay, and I'll motivate this with the connection to Schatten classes later, right? So for the moment, we know that this kind of inequality is related to Hilbert-Schmidt.
Some hard inequalities where it's distance to boundary that plays this role.
Yeah, but they're kind of different because this is like on the Fourier side, right? So there are these kind of inequalities, right, which are also confusingly called Hardy inequalities sometimes, but it's a different kind of Hardy inequality than this. There is, yeah, but this kind of different because this is for functions with Fourier support, right? This is for a rather small class of functions in a way. So this problem is somehow much more rigid, and you can expect sort of stronger results. But it's not on the space side, it's on the Fourier side. So it's quite different actually. But yeah, thank you for your questions. It is okay. So one result is this. So if you take a polytope, right, and polytopes in dimensions 3 and higher can be kind of complicated actually. So so it's not that this is, yeah, so yeah, in 2 dimensions, of course, this is not so surprising, but in higher dimensions, polytopes are not so simple. Okay, so we have kind of the natural, okay, the details are not so important, but we have sort of the natural, or maybe the details are important, but I don't want to discuss them too much. But at least, okay, you get the Hardy inequality, and you get the Q, okay, you always have the Q equals 2 inequality, because that's just Plancharel for Q, is it called Plancharel? For Q equals 2, okay? Okay, so how do you, so in particular the Hardy inequality holds, and how do you do that? Well, okay, so for simple polytopes that locally look like a simplex, this is just like this kind of octant case, right? Okay, this could be 3 dimensions. And in this case, it's just a tensor of what we already know. It's like a tensorization of the usual Paley Wiener space. So it's not hard, just some writing that AI can do to go from, you know, interval to that. And then you can approximate general polytopes by simple polytopes to get the Hardy inequality for all polytopes. And then actually, even though, so in this case, you don't have bounded projections at the endpoint, but you can actually interpolate in this setting. And then but for the Paley Wiener spaces. So then, yeah, let me not talk about why that is, but you can actually interpolate despite not having a projection. And so then you can get like a wider range of inequalities from there. So, so it's kind of nice to have. On the other hand, for the ball, this is not, things do not work the same. So the ball is different, right? Like I said, there's no bounded projection for any LP on for the unit disk or for the unit ball. That's the famous result of Pfefferman. So you would maybe expect things to be different, and indeed there are. So in this case, for example, this kind of Hardy inequality does fail, and the proof follows this kind of scheme from like Kakea type sets, Besikovic type sets. So what you do is that you look at a level set of the weight function. Okay, the weight function is just like a distance, power of a distance, like you said. But you should look at a specific level set that respects the geometry kind of. It's actually kind of hard to draw because this annuli should be thin, but this annuli should be sort of, so you put like thin boxes here in such a, so this is like a level set where the omega function behaves like n to the minus n plus 1, and then you put n such thin boxes around here. So this is like a standard technique. So those boxes have dimensions n minus squared times n minus 1. Okay, so you try to basically put some, I mean, you can't put characteristic functions because we wanted to play well with the Fourier transform, right? But you put like, so we put a natural number of boxes here, which will be n if you compute things. So you have n boxes. And so you want to put some functions on these, right? So you put some Gaussians, right? And hope that they don't interact much. And then on the Fourier side, each such box, so these have dimensions n minus 1 over n squared, 1 over n. So on the Fourier side, this will turn into really large boxes, right, of different directions with dimensions. I don't have space on the board to draw them all because they turn into large boxes instead, right? They'll turn into n squared times n boxes. But then you have here the freedom to move these, right? Because moving these, translating these amounts to, on the Fourier side, that just means to multiply by a unimodular factor, right? Like the character of the, e to the ix y or whatever. So, and that doesn't change this inequality because you have absolute values in there. I mean, if you think of these as all as characteristics, you don't change this side at all by modulating here. But on this side, you move these all together. And so then by modulating shifting, you can, so maybe you've seen this before, you can have this kind of construction where you get these boxes to overlap quite a lot. Well, okay, that was not, okay, they can overlap more than this, but so the point is somehow that if as disjoint sets, we have n of them of dimension n third, so you would expect like the total area to be n to the fourth, right, if these were completely disjoint. But after modulation, you can actually pick up this extra logarithmic factor, so that makes this strictly smaller than n to the 4. And using that kind of thing, so this is like a standard type of thinking in this Kakeya set phenomenon, you can actually show that this can't be bounded. There is the like additional complication that you have to understand an LP norm, but what you do is like you put random signs and then you use Kinshin inequality to deal with to that randomness. Okay, so this is basically the same method that, or this is the same method that Pfefferman used to disprove the disk conjecture, just for a slightly different, for a different problem. And there's kind of a converse. So, okay, so these sets here were used in the construction originally of like Besikowicz sets. So a Besikowicz set is a set that contains every direction but has measure 0. And then the natural kind of question was, well, what is the dimension of such a set? And in 2 dimension, it's kind of elementary to see that it has to have full dimension, like in Hausdorff dimension. But in higher dimensions, it's a really difficult problem. And this problem is actually connected also in the other end, right? So if you think like in many ways, the Hardy inequality feels somehow sharp, or would be my guess. But if we had the weaker ones where we lower the power a bit, then you would actually, the full Kakeya conjecture must be true, right? So it's actually sort of stronger than the, I mean, formally stronger than the Kakeya conjecture by a similar kind of argument to this. So the Kakeya conjecture was proven like last year or something in n equals 3. I don't know, but yeah. So it asks basically that okay, you can lose a logarithm here, but you can't lose the whole power of n, and that's what it asks for. And if you actually had, if it, like naively, I thought that I would prove this for d less than 1, and then when you write all the details, you realize that actually it implies the Kakeya conjecture, and then you think, okay, I probably can't prove this. But anyway, it's a nice connection. For the Helson inequality is the one that I had before, where instead with the weaker inequality, where instead of a 1, we have a square. That's weaker because we're in a bounded set. So so it's always the infinity norm of the Fourier transform is always less than the 1 norm. So this kind of Helson inequality is weaker. And one criterion for that is the same one I had this function b earlier. And you would have the same kind of criterion here, but with 1 over this weight function, right? If there is a c that is a bounded function and its Fourier transform is some wild distribution, possibly, but inside omega, it coincides with 1 over your weight, then you would have the Helson inequality by the same argument that I wrote before. Like you would write this as a scalar product of f hat times c hat, and then you would do, then you would do the Plancherel. No, I keep mixing up the names. I'm sorry. And you would get the inequality. And for the ball, this is actually true by this kind of concrete application calculation that I'm not. I wouldn't have pulled this out of my own hat, but this is easy work for Claude or OpenAI or whatever. Like this is basically in like Gelfand, and what book of Gelfand and Shilov, where they study such things. So you have to be a bit careful here what this. So it's like you take this kind of Bochner kernel and you define some limiting version of it. And then the power here is not a power, it's like defined via analytic continuation. But then it turns out that you actually can get a Fourier transform that has this property, and like on the space side, it's some Hankel function, which is bounded. Okay, this is.
You say it's easy work for Claude or something like this, but did it tell you the reference, or because you want to cite like Gelfand or something? But when you asked Claude or something, did it tell you that you should cite Gelfand or something?
Yeah, it gave me the reference. Yeah, but it had a very long very unnecessarily long thing of putting this together with different sums and stuff. And I couldn't really understand what it did, but it gave me the right reference, yeah. And then I read Gelfand, or well, few chapters. Okay, and I'm saying a lot, so let me not say this, but it's, even though I don't have interpolation for the Paley Wiener spaces, I don't know, there could be interpolation, that would be a very interesting result, but we do not have bounded projections, so it doesn't follow from just projecting LP, but it's still possible to do something by doing like, yeah, Hadamard 3 lines theorem, but okay. So this inequality that is really the Karl-Mikael inequality, and which is really the isoparametric inequality, why do I call it the Helson inequality? Well, because Helson was interested in this, in the connection with Hankel operators on these large Hardy spaces living in a, with functions with Fourier support in a cone. Okay, so I'm just recalling the calculation here, that the S2 norm was given as a square integral against that weight. Okay, and you can think of this as kind of some sort of Sobolev space or something with respect to this weight, right? And then it's natural to think here that, well, okay, if you then take the dual with respect to the L2 pairing, you would obtain, right, the opposites with a minus in the weight, right, where you would have 1 over the weight. Sorry, I gotta drink some water. Okay, so what does the Helson inequality say? Oh, I'm talking too fast. So, so the Helson inequality says, right, that this weight here. Okay, I mean, if the Helson inequality holds for omega, it holds for 2 omega. That's easy to see. With some constant. So that's the Helson inequality. So, and actually this is for Paley Wiener functions, right? So let's write it like this. So in other words, the Helson inequality says that, what does it say? If we call like this, like a norm, then it says that PV1 is included in this Sobolev type space, right? But now if we take the dual of that, so if I look at the duals, if I just dualize this, it says that H star is embedded in the dual of the Paley Wiener space. But H star, the dual of that norm is precisely this norm, which is the S2 norm. So so this would be like the space of Hankel, S2 Hankel. I mean, okay, so the space of S2 Hankel operators is this dual space, which is in PV1, which is a subset of L1 star by Ham-Banach, right? Any functional on PV1 will be a functional on the L1, which is L infinity. Okay, so this was kind of formal blah, blah, blah. But what this really, okay, so now, sorry for my terrible handwriting. I was not, my teachers did not like me in school. But if you work out what this truly means, it means this. So, okay, so assume if we have the Helfand inequality, if an operator is in Hilbert-Schmidt, then there is a infinity symbol whose Fourier transform must coincide with the symbol for the Hankel. And in particular, this is true on the ball. So I would say that any Hilbert-Schmidt Hankel operator for the Paley Wiener space of the ball has a bounded symbol. And I call this like S2 Nahari theorem, because this is a classical thing so this is like a very weak form of the Nahari theorem. I mean, I'm happy to know it, but it's very weak compared to the actual Nahari theorem. So a full Nahari theorem would say that if the operator is bounded, if the Hankel is bounded, so not only, Hilbert-Schmidt is much stronger than bounded. So the Nahari theorem says that if it's bounded on Paley Wiener of omega, then there is a bounded symbol, right? This bounded function whose Fourier transform gives you the symbol. Okay, and I call it this after Nahari, who proved it in the classical Hardy space setting, which Rochberg then localized to the Paley Wiener setting, which requires some argument. Okay, so that's the classical theorem. And okay, and like I kind of alluded to earlier, that this is not known for the Hardy space in the product setting. Neither is it known for the Paley Wiener space of the cube. And this I would identify as like the biggest outstanding problem in multi-parameter harmonic analysis. Maybe I shouldn't have agreed to the recording, because the story is, do you know the story? So the story is that this was a huge problem in the 80s and 90s, and Pfefferman's working on it and so on. And it was finally resolved in it wasn't, but it was believed resolved in 2000. And there's a very important ACTA paper, trying to resolve this question, and then it was accepted, and then it was used as like a big black box in a lot of multi-parameter harmonic analysis. Like a lot of results were built on that. But then around 5-6 years ago, there was someone found a very fundamental flaw in this proof of this, and so it's been an open problem since then ever again. So what I've been using, I got my university to pay for a lot of tokens. So I've been trying to use it to create an overview, because there's a lot of very good and important mathematics in those papers, right? Like the ones that build on the black box and the original resolution of this problem. So I'm trying to figure out what we actually know, right? Like what do we, from all those, try to.
Who was the paper?
Sarah Ferguson and Michael Lacey. But yeah. And yeah, people have tried to fix it. And so I think the problem was pointed out by Sasha Wolberg and Trail, who worked on this problem.
The people accept the mistake.
Yeah. This is fully integrated into the. I'm not a rebel trying to say that. No, and there's a concrete counterexample, and and it's kind of. The authors accepted, yes. There's a corrigendum. Ish, but they do accept it, yes. Maybe we don't record this. Anyway, so yeah, please. Okay, so anyway, so here is a much weaker theorem, right? That if it's in S2, then we have the Nahari theorem. Okay, and this to me suggested, that this is kind of like, like a Sobolev type norm. So let's try to define some kind of like, okay, let's actually, best of space type spaces adapted for this Paley Wiener setting. Okay, for classical Paley Wiener that already exists and so on, but let's try to do it for the ball, for example. And I'm not going to torture you with the details, obviously, but this was actually, so this is the, very bad supervision on my part, because I gave this like as a nice problem, first problem to my PhD student Kostas, and it turned out to be a very difficult problem. And so now in the end, we have this, after 3 papers, we have this very nice, the correct framework, because there's only 3 conditions and every convex set satisfies them. But in the, the first versions of this had 10 conditions, 8 of which were natural, but it wasn't clear what implies what. And, it was a very misguided first problem to give to a PhD student. But luckily for Kostas and for me, he's a clever guy. So anyway, so you should try to define your best of spaces with respect to these level sets. That's kind of clear, right? So you want to single out, these level sets here of the weight, and you want some kind of subsets of this, and I want to choose basically rectangles or maybe parallelepipeds if you really want, but let's say rectangles. And the condition on what should be a sort of cover to define a best of space on, now in the final smooth version, are just these 3 things. The first just says that the boxes cover the set and a little more, right? Like they still cover if you make, so this is the affine map from that square to the unit square, that rectangle to the unit square. And these should cover your set, rectangles covering your set, right? But they should still cover if you make them a little smaller. That's an okay condition. The second condition says that that if you have 2 adjacent pieces in your decomposition, then the transition map is uniformly bounded. That's what this says, because it says that it maps one into the unit ball of the other. So that means that they're oriented roughly the same. So that means when you're, you have your set, I don't know so many convex set, but when you're in your, you have this, so here would be like a hyperbola, and here would be like I should have more colors here. But when you're in this kind of level set, this condition just means that if you have 2 adjacent boxes, they shouldn't have wildly different orientation to ruin this condition, right? Like the next box should be not so far from, have roughly the same orientation as the previous one. And then you have this natural condition that if you take the sum of, so this is kind of like a grid for your whole, I can't draw it right now, but this is like a grid for your whole set, right? And in Rn, this would be exactly just a grid. And if you take the sum of 2 of them, they should not intersect too many other boxes. So those are the natural condition. And what's more is that, okay, so every convex set has such decompositions. So it's nice. And there can be constructed in a very canonical way. You just take the level sets, you take a point, you fit as large a box as possible. You continue doing that until by induction, Zorn's lemma, you're done, and that gives you a decomposition. Okay, so yeah. And then once you've done that, then these properties with the transition maps and so on, ensure that for your decomposition, you can choose a associated partition of unity which has uniformly bounded L1 norms so that it works well with Young's inequality and you can do things. And then you can define Bezow spaces. Remember, a to the minus j is like the weight on the Fourier support on this thing. So here is really, it's the weight here, a to the minus j is the weight on the Fourier side of this. So you define a Bezow space that looks formally just like your usual Bezow space with respect to these functions. But in the usual Bezow spaces, you have rings, right? That's not what you have here. So maybe I should try to draw something after all. So right, in Rn, in a usual Bezow space, these sets are like supported on rings, but on the disk, for example, these are supported in. I really wish I had different colors, but and maybe I do. These are instead supported on, on grids like this. Okay, so for the disk, this decomposition is what you think that it is. So it's a different decomposition, and one of these should extend. I can't draw. I should have prepared this ahead of time. But okay, but you understand what I mean. You split this into small sort of dyadic pieces, so Carlson squares basically. So it's not the usual Fourier space where the Fourier support is on rings. Here it's on smaller squares. Sorry for the horrendous picture. So bad. Or on the square, you would just, maybe I can draw it better on the square, right? On the square, you would divide things like this, right? Into little squares. And here you would continue like that, and this, and right? So you would define everything into little squares. Okay, so it's quite different from the usual Bezow spaces, but formally it looks the same. But the Fourier support is with respect to these little squares on the Fourier side. And then in particular, then if you account that this is the weight in the Hilbertian case, this recovers these two norms that we saw kind of naturally. Okay. Okay. Okay, so it is. So it's natural, and this is what Peller does and what Rochberg does and so on. It's natural to consider sort of a class of, so you can maybe interpolate later to consider not only Hankel operators, but to put some weight on the Fourier side. And of course, we should put powers of our weight. And then it's fairly straightforward to see the necessary part, that's standard, that if it's in Schatten class, then it must belong, if this weighted operator is in the Schatten class, it must belong to this kind of associated Bezow space. And for the converse, in this general setting, it's kind of dissatisfying. It's only for between 1 and 2. And okay, so the trace class argument here is pretty nice, I have to say. Like, I don't have time to explain it, but I'm very happy with the trace class endpoint of this argument. It's like a pretty big generalization of the Peller method to integrating some convex analysis. And then at S2, of course, you have at p equals 2, you have like a condition. But the funny thing is that the S2 condition does not come with a sharp range of indices. I mean, that sounds crazy. I couldn't believe it that we don't understand the Hilbert-Schmidt setting fully here. And it has to do with the fact that to understand the Hilbert-Schmidt setting, you have to understand the convolution of this, I will finish, don't worry, of this weight with itself, and we kind of don't. So the Hilbert-Schmidt case is not fully understood. Anyway, so, but for Hankel operators where you have no weight, okay, these things are equivalent in the range 1 to 2 at least. I would really like 1 to infinity, but we have 1 to 2 in general. Okay, but again, this is kind of technical stuff, so I wouldn't try to, go into it too much. Okay, and then for the ball, or more generally any strongly convex domain, so smooth domain with strictly positive curvature on the boundary, you can extend this. You can prove sort of an endpoint result that's like a weaker endpoint result and try to interpolate. And by doing that, we arrived with this P as the restriction. But I don't think that's natural. It's just like an artifact of the way that of the operator we constructed at infinity and tried to interpolate to. So it's not, even though we worked hard on this, it's not. So I mean, it has a lot of nice stuff in there, but I would really like this result for 1 to infinity. Okay, and then for polytopes, okay, it's not, well, for general polytopes we don't know. Actually, I don't understand because, right, a polytope in R3 can be like, a pyramid, right, with a square base. And so this could be a polytope P. And for that kind of polytope, the weight is not that easy to understand. It's like a sum of distances to the supporting hyperplanes, like sums of products of distances to the hyperplanes. And it's not that easy to understand. And it's, I think, interesting. There's a lot of connections between the things I've been talking to and like stuff we found in convex analysis where they study these types of things. So pretty nice. But for simple polytopes, which behave like the classical Hardy space, okay, then you have the full characterization for all P, and that recovers like classical results. Okay, so my motivation was that I did S2 Nihari, right? And then I said, okay, so let me invent some Bezo spaces. So let me have SP Nihari. And okay, and I have that, well, only for the Hardy space in 2 variables, because in this higher dimensional settings, 2 variables is much easier than 3 variables because of the geometry. And therefore, I have it for Paley Wiener spaces of polygons, but not for in higher dimensions yet. So if you're like a harmonic analyst specialist, which I don't think you are, then what this result says is like an embedding. Now that we have that this Bezo space is embedded in product BMO, or product bounded mean oscillation, and that's product BMO is like another way to phrase those Nihari type things. It's like the natural L infinity endpoint, right? Interpolation theorems don't work with L infinity, so what's the endpoint? Well, you should put something called product BMO, but let me not get into it. And yeah, I'm gonna finish up. There's actually like, so you could ask then, I mean, this result doesn't tell us anything new, but it's just a nice connection that if you have this kind of Bezo space, characterization of SP, then having SP Nihari actually implies this kind of some of these Hardy inequalities. So it kind of goes both ways. So these problems are really intimately connected. So in the end, it's not like I'm trying to give a talk about 2 different things. I'm really giving a talk about some connected things. And I just had a slide to mention that like these 2 variables and then even 3 variables are much more difficult, simply because in dyadic intervals either contain each other or they don't intersect. But dyadic rectangles, that's true. They can intersect without, just one side has to be contained in the other. And one standard tool that is a very important tool due to Journet is this kind of Journet lemma, which has sort of discusses how much you take an open set and you consider all the maximal dyadic rectangles, how much can they intersect? And okay, let me not go into that, but that's kind of a key thing to use in these kind of things. Okay, thank you.
Thank you very much. Any questions for Khaled? No, there were some during the talk, so it doesn't look like.
No,
Okay.
but it was slightly difficult.
So let's again.